In this video, I want to talk about why I don't believe in large coefficients. What do I mean by that? I mean that if I run, for example, a logistic regression model, right, and I run my gradient descent, stuff like that, and that would be the logistic regression model where I say that I'll assign this kind of probability, which would really be an estimate for how much I believe that yi is equal to 1 using this kind of formula. So if I run that, I'm saying that if one of the thetas turns out to be really, really huge, I'll say, well, it's probably a bug, or it's overfitting, or it's something that's probably not the right theta. So another way of saying it is that I have this prior on my theta's j's, which is, well, like maybe something like that, where if theta j is larger than that, and just say, well, something went wrong. I can, of course, kind of officially incorporate it into the model using, for example, L2 regularization, as we saw in class. So anyway, why do I not believe in large coefficients? Well, here's one reason. Here I have a data set, so it's not a very large data set. So we have one data point, and then we have another data point. Here it's 1, here it's 0. And what I want to focus on is the value of theta 1000 that we'll get if we use maximum likelihood in order to estimate the thetas, right? So how's it going to go? Well, let's just write the log loss. So let's write essentially the likelihood of this data set. What is it going to be? Well, it's going to be the log likelihood of this data point. So that's just going to be theta transpose x1, right? And then we'll make it be like that, and we'll just take the log. And then we'll say plus the log likelihood of 1 minus sigma x2. So when we are learning with maximum likelihood, so when we are trying to find the best theta, what are we going to do? Well, we're just going to try to minimize this. Why is this correct, by the way? Well, this is just the log of the probability of this data point, because here I'm talking about the probability of y equals 1 conditioned on this x. And here I'm talking about 1 minus the probability of y equals 1 conditioned on this x. Why 1 minus? Well, because here y is equal to 0, so the probability of y is equal to 0 is just 1 minus the probability of y being equal to 1. So what's going to happen when we focus on theta 1000, which multiplies this guy, when we are computing this? So, okay, so x1000 is equal to 0 over here, which means that this term basically doesn't matter. We're just going to be concentrating on this term, right? And we're going to try to maximize it. For which theta 1000 is this guy going to be maximized? Well, this guy is just log of sigma theta 0 plus x0 plus 1 plus theta 1 x1 and so on plus theta 1000 x1000 1. And this guy is 1. So the larger theta 1000, the larger this term is going to be, which means that if we use gradient descent, theta 1000 is just going to escape to infinity. So this would be obviously an extreme case of overfitting. The reason it's going to escape to infinity is because there are no examples here where x1000 is 1 but y is 0. All right? And that's the kind of thing that would tend to happen if you have essentially lots of dimensions here, lots of x's, but just a few examples. And this would be an example of overfitting. So even though here, if we just use maximum likelihood and just maximize this, we'll get a theta that's extremely large, actually theta that will be escaping to infinity. That's not something that we should believe. And this is not something that we would believe if we had this kind of prior.